Okay, now we will take a third function e to the power of minus alpha t u t. Then we take the Laplace transformation. Now, e to the power of minus alpha t u t of course is 1 in this range of integration, e to the power of minus s t dt, which is equal to 0 minus to infinity e to the power of alpha plus s times t dt, which is equal to e to the power of minus s plus alpha times t divided by minus of s plus alpha evaluated between the limits 0 minus to infinity. Now, once again we would like to make the integral converge at t equals infinity by making sure that the real part of s plus alpha is positive number. Real part of s plus alpha must be greater than 0. So, when you make that, if real part of s is greater than minus alpha, if the real part of s is greater than minus alpha, at the upper limit real part of s plus alpha is greater than 0. Therefore, at t goes to infinity, this integral becomes 0. This the limit of this at t equals infinity will become 0. At the lower limit 0, this will be of course equal to 1. Therefore, it will be, and this is a minus sign already here. Therefore, this will be 1 over s plus alpha. So we have, yes, for a function e to the power of minus alpha t u t, the Laplace transform is 1 over s plus alpha, and this integral will converge provided the real part of s is greater than minus alpha. We are taking alpha to be real in this case. If alpha is real, this is what we have. Now, as far as this integration is concerned, it does not matter even if you are taken e to the power of minus z t, z is complex, then we go to the same argument, same analysis, it will be 1 over s plus z provided the real part of s is greater than minus of the real part of z, the real part of s plus z is greater than 0. So, even if this is z t u t of course. So, alpha need not be real, it could be even a complex number. Even if z is complex, the same relationship will be valid. So, I will write here e to the power of minus alpha t, alpha real 1 over s plus alpha, this is minus alpha, minus z t, z complex 1 over s plus z minus real part of z. So, once we have this relation, then we can find out the Laplace transformation of trigonometric functions. Suppose I take cos omega naught t u t. This can be written as 1/2 of e to the power of j omega naught t u t plus e to the power of minus j omega naught t u t. And since we have found out that e to the power of z t minus z t will have 1 over s plus z as its Laplace transformation, then we have instead of z we have j omega naught. Therefore, the Laplace transformation of that would be 1/2 of 1 over s minus j omega naught, because e to the power of minus z t had the Laplace transformation 1 over s plus z. Instead of minus z you have j omega naught. Therefore, you have s minus j omega naught, and the Laplace transformation of this would be 1 over s plus j omega naught. So, if you complete this, this will become s over, when you rationalize, denominator will become s squared plus omega naught squared s square plus omega naught squared, and the numerator will be 2s, and divide by 2, this becomes s squared omega naught, s by s squared plus omega naught squared. In a similar fashion, if you find out the Laplace transformation of sin omega naught t u t as 1 over 2 j e to the power of j omega naught t u t minus e to the power of minus j omega naught t u t, that is after all the sine function can be described in this fashion. This can be written as 1 over 2 j 1 over s minus j omega naught minus 1 over s plus j omega naught, exactly in the same fashion, and in the numerator you get 2 j omega naught by rationalizing the denominator, and this 2 j will cancel with this. So, you get omega naught over s squared. So, that is what we are having, and in this derivation we would, the abscissa of convergence should be the real part of z. This is the running with z. The real part of this is 0, that means the abscissa of convergence for both these is 0. So, we have the final result cos omega naught t. I can write this as omega t, because as long as you do not confuse this omega with the real imaginary part of s, we can as well write cos omega t, or if you like we can still continue cos omega naught t, then we can write this as s over s squared plus omega naught squared and sin omega naught t. This is of course always this u t continues with us, because we are assuming this function to be 0 for negative values of time. This will be omega naught over s squared plus omega naught squared, and the abscissa of convergence for this is 0. So, that is what we are having for the sine function and the cosine function, which are truncated at t equals 0. That means, the sine and cosine exist for only for positive values of time. Now, we can represent the poles and zeros of these f of s in the complex frequency plane. For example, for these are all rational functions of time, therefore, they exist, the poles and zeros exist for this. As far as delta t is concerned, it has neither poles or zeros. As far as u of t is concerned, there is a pole at the origin. As far as e to the power of the Laplace transform e to the power of minus alpha is concerned, 1 over s plus alpha, therefore, there is a pole at minus alpha. Forget about this z. Taking these, you have for the cos omega naught t and sin omega naught t, there are 2 poles at plus omega naught and minus omega naught. The zeros will depend upon the cosine function or the sine function as case may be. And now, you observe that the abscissa of convergence in all these cases, this is 0, the abscissa of convergence is 0, therefore, the region of convergence is the region to the left of the rightmost pole. In all these cases, you will observe that the region of convergence, which is defined by the abscissa of convergence, is the region of convergence is to the right of the rightmost pole. In this case, is the rightmost. There are only 2 poles. That means, entire region to the right of these poles is the region of convergence. The entire region to the right of this is the region of convergence. The entire region to the right of this is the region of convergence. That means, the region of convergence is defined by the extreme pole, the rightmost pole that you are having for the particular function. More about this we will take up in the next lecture. To summarize what we have done today is, we said that Fourier transforms of certain time functions which grow exponentially do not exist, and to take care of such situations we can think of introducing a convergence factor e to the power of minus sigma t. So, instead of finding out the Fourier transform of f of t, we can think of the Fourier transform of f of t e to the power of minus sigma t, and then try to find out the inverse Fourier transform and reintroduced cancel out this e to the power of minus sigma t, which we introduced in the first place. So, both these formulas which we have lend themselves to the Laplace transformation formula becomes, we do not have to introduce e to the power of minus sigma t artificially, if we introduce a new variable s, which is sigma plus j omega. So, the Laplace transformation evolves from such considerations, and we have f of s, which is given as f of t e to the power of minus s t integrated from t from minus 0 to infinity, and inverse Laplace transform is 1 over 2 pi j c minus j infinity to c plus j infinity of f of s e to the power of s t ds. And this integration is along a vertical line in the region of convergence. The region of convergence is defined by the half plane where the real part of s is greater than a particular value which is called the abscissa of convergence, and this abscissa of convergence depends upon the particular function that we have on hand. And we then took up the consideration of Laplace transformation of various important time functions. In particular, we found out the Laplace transformation of the impulse unit impulse function at the origin, which happens to be 1 itself, the Laplace transformation of this unit step function, which is 1 over s, a particularly simple relation, and e to the power of minus alpha t u t, the Laplace transformation of that is 1 over s plus alpha, and then cos omega naught t and sin omega naught t give reduced to simple Laplace transformations of this type, s over s squared plus omega naught squared and omega naught over s squared plus omega naught squared. We will continue this discussion in the next lecture by enlarging the class of functions for which we find the Laplace transformation, and also we will look at some of the important properties of the Laplace transformation as such.